Thank you, Simon. Good evening, everybody, and thank you for inviting me. I hope you enjoy this talk tonight. This story starts in Labrador, so we're going across to the other side of the Atlantic. You can see on the screen here just a very simplified picture of what's called Lake Agassiz, and this is a post-glacial lake, and it's got this ice dam barrier in the shape of the Laurentide ice sheet to the north. What happens is, due to rising temperatures, the ice dam fails, and all this very cold glacial meltwater escapes out into the North Atlantic via the Labrador Sea there, Hudson Bay on the way. So what we're going to do tonight is I'll extend on that in a moment, but is explore the combined impacts of these abrupt climate change events, as well as against the background of rising sea level that's happening at the time anyway, due to increasing temperatures through the Holocene. So here's another diagram. Again, so there's our Lake Agassiz. You can see where the water escapes to the north. There's the Atlantic Ocean and the British Isles over there to the east. And what basically happens here is that when the cold water comes out into the North Atlantic, there's several things take place. First of all, there's a jump in sea level. And it's estimated that's around 1 metre plus in the North Atlantic, but also elsewhere around the world. So this is a huge, huge event. It also puts really a stop to the thermohaline current in the sea. Basically, the Gulf Stream, or the North Atlantic Drift as we know it, that starts off in the Caribbean, the cycling of warm water drags with it warm air all the way across the Atlantic and washes the British Isles, particularly on its western coast. When this cold water comes in, you get a kind of cap of cold water, and that disrupts that thermohaline current effect and effectively stops the North Atlantic Drift. So this drops temperatures as well. The consequences of that, as you'll see later on, means a reduction in tree cover, particularly around northern Britain. We can see that in the pollen records. Drier conditions, much colder conditions, and much more windy conditions. And this clearly has had an effect on human populations. It's been invoked for all sorts of things. I think some less evident than others, let's say, but it's been used to invoke the spread of farming from the Near East at this time, because obviously they start farming earlier. But what we're interested in tonight is particularly looking at these Mesolithic populations. This event dates to somewhere close to around 8,400, 8,500 BP before present. So all the dates I refer to tonight will be BP before present in calibrated calendar years, okay? And so what happens, this climatic downturn, if you like, is referred to as the 8.2 event, but it spreads over a longer period. It's not as kind of tightly defined as that. So it starts a bit earlier as a consequence of the breach of the ice dam wall, and that sets in train this kind of cold snap, or neoglacial, as these are sometimes called. So let's just, in terms of geography, let's just take a quick look at where we are. So this is quite an old map now, actually. It was produced in the National Geographic magazine. And you can see the pale green identifies the edge of what is pretty much the continental shelf on the edge of northwest Europe there. And you know, at when the ice began to melt at the end of the Pleistocene, this would have been dry land. But obviously then as sea levels rise, the coastline retreats, and you can see where they've estimated in the pale green around 10,000 BP. So that's the time of the, for example, the Howick house, but also sites like Cramond and Ecklin and so on. And then you've got one at 9,000 BC in the darker green, and you can see the Dogger Bank area here is identified as an island by that point. And then, of course, as time goes on, this land between Britain and continental Europe also becomes drowned, and Britain becomes an island. So this story is also, relates to our island history. Okay, so let's just look at that 8.2 event. So the top graph here is one of the Greenland ice cores, and you're looking at the oxygen isotope measurements there. And the one I've highlighted in red is showing that downturn here that represents the 8.2 event. There's one to the left of that over here. This is 9.3, and this is an important neoglacial as well. But it's not the focus of the talk tonight, but that's another one of these neoglacials that does require some investigation and further work on to try and understand the impact on human populations as well. But you can see 8.2 is the big one, and that's what we're going to focus on tonight. The graph below, this is taken from Sturt et al., important paper they did 2013, reconstructing sea levels. There's been a lot of work on this over the years, the important work of Shannon and also Bradley and so on since then. But what this graph shows, this is based on a GIS model and using what are called sea level index points, where the dating sort of organic layers at past sea level, so usually from the intertidal zone. And they're using that and interpolating based on taking into account sort of eustatic sea level change as well. The amount of land that's being drowned in 500-year blocks. So let's look at that in more detail. So you can see it there. That's the period we're interested in, 8,500 to 8,000. And you can see there's a sudden big jump in the blue bar. The blue bar is one we're interested in because that's the North Sea area. So a huge amount of land being lost during that period, around 18,000 square kilometres, and this is gigantic. A lot of that to do with the failure of the ice dam and the sea level rise due to the draining of Lake Agassiz. Okay. Well, my first encounter with the tsunami took place at Howick. This is on the Northumberland coast. It's a beautiful setting. It's sort of south to mid-Northumberland. And it's a fascinating site in many ways. It was discovered by a gentleman walking his dog, walking along the top of the cliffs there, and he saw this erosion scar, and he found some flints in it. And I used to do a kind of roadshow event with a colleague of mine, Lindsay Allison-Jones at Newcastle, where we'd invite the public in, and it was a bit kind of antiques roadshow style, but for archaeology. So people would bring their finds in, and we'd talk about metalwork and flint and pot and so on. And then the afternoon was identifying things for people. And this chap came in with an envelope with flints in. And I took one look at them, clearly Mesolithic, a couple of scalene triangles, beautiful stuff. You know, at the time, what everyone would say is late Mesolithic, narrow blade. And I asked him where he got them from, and he described it to me. And he said that, they came out of this sand in the eroded sort of cliff section. And I said, and he said, and there's a field effectively on top of it, And I said, hang on, do you really mean the sand or do you mean the soil? And he was insistent. He said, no, it's definitely the sand. So I was really interested because the implication was you could have in-situ archaeology. So I said, look, I'll come out and visit the site with you. So I did, scraped down the section, and sure enough, flint was coming out the sand below the plough soil. And on the back of that, we did a small test pit, 1 metre square, came straight down onto pits, rammed with charred hazelnut shells, loads more flints. We clearly had a site on our hands that was in situ and undisturbed. And on the back of that, we launched a project from Newcastle University at the time, and got funding, particularly from the Heritage Lottery Fund, and did 2 phases of excavation, an initial phase in 2000, and then the big excavation in 2002. Ran that with my co-directors, Nicky Milner, who's now Professor of Archaeology at York, Head of Department, and also Jeff Bailey. So what we can see in this picture, on the left-hand side, you've got the Howick pit house. There's 3 very clear phases to that. But then from the aerial shot that you can see on the right, this was taken, I took this from kind of like a cherry picker, and you can see, looking southwards, you can see down the coastline to the Howick Burn, which is the valley you can see in the middle distance there, with the tree-lined, deeply incised valley opening out into that estuary, where the Howick Burn falls out into the North Sea. And down in the base of that valley, myself and my colleague Ian Boomer, he's now at Birmingham University, associate professor there. Ian is a coastal geomorphologist, amongst many other things, and we'd worked closely together for some years. And we decided to have a go at trying to find some paleoenvironmental evidence to go with the Mesolithic site. So we started coring in the valley as well as down the foreshore. And we used a vibro core. You can see it there, bottom left. And we got it down 7 meters, and then we hit a sort of hard obstacle. And we thought, probably hitting bedrock. But myself and Ian, we said, well, let's give it another shove for good luck. And so in it went again, and we, really whacking it down to try and penetrate it. And sure enough, it bashes through and goes again. And we get more soft sediment from below. And we looked at each other because both of us were thinking the same thing. And just turned around and I just said to Ian, tsunami. And because obviously the idea of hitting some coarser sediments within an organic soft sediment profile was quite unusual and odd. So anyway, we extracted it all, and you can see these lovely laminated sediments on the right there. I mean, they were exquisitely preserved. Great pollen in there. We've got a really good sequence of carbon dates all throughout the entire sequence, as well as other organic organisms, so, ostracods and foraminifera and so on. And there is the offending clastic deposits. That is a tsunami. And that was reached at about 7.2 meters or so below current land surface. And you can see it's very coarse material. And this is probably the coarsest material that's been found from the Storegga tsunami, if you exclude the huge boulders that have been catapulted up onto the top of the cliffs in the Shetlands. You can see then the very sharp contact with the silt sediments, which immediately underlay it as well. So let's just look at the Storegga tsunami. So an area, broadly speaking, the size of Scotland, on the edge of the continental shelf, the Norwegian Trench. Effectively, the material on the edge of that fails and slides down into the Norwegian Trench. It's the biggest megaslide tsunami that's been found on planet Earth, certainly during the Holocene. This is no trivial event. It is one of the biggest tsunamis ever recorded on the planet. And the cause of it, it's still not settled in its entirety, but probably a combination of overpressure from the additional water because of the draining of Lake Agassiz. Also, possibly a change to the clay structure, the matrix that's holding these shelf edge deposits together probably with some seismic activity, leads to this huge slide. Now, it's directional. You can see that it's facing the southwest. So the Faroes, the Shetlands, they're right in the line of this. And evidence for the Storegga tsunami has been found all the way across the other side of the Atlantic in Greenland. You can see from that diagram that the areas which are going to take some of the serious force from it is northern Scotland and the northeast coast of England as it kind of funnels down into what in effect at the time was more of a gulf, the North Sea Gulf, necessarily than the North Sea as we know it today. Because even if by that point, due to rising sea level, Britain had become an island, which is not entirely settled yet, but Britain is more or less an island by that point, the ability for, in a sense, the wave to escape is limited because you're going into what is effectively more of a gulf than a big open sea. And of course, you've also got Dogger Island in there, probably about the size of Wales by that point, but together with probably thousands of small islands and islets all around the sort of East Anglian coast, sort of across then to the Low Countries and all across the German Bight and up through Jutland. We'll talk about that a bit more in a second. So these are Sturt's maps with his model sea level. And the one we're interested in, or the two we're interested in, is bottom left. down here, but also this one at 8.5. So this kind of period between 8.5 and 8,000, they're 500-year time slices, these maps, are the bit relevant to us. And you can see here that according to his model, you can see Doggerland out there in that darker green, the sort of the big Dogger Island where Dogger Bank is today, together with a potential land bridge still connecting across there, possibly not breached by 8,000, but certainly by the time the wave comes, we can be pretty confident that Britain, for all intents and purposes, is by that point an island nation. Well, I say nation, an island land block. The shaded bits, by the way, represent a lot of these small islands. So to simplify that map, there's a close-up of it, just sort of redrawn it to give it more simply. So this is the kind of configuration we've got based on those Sturt maps. And I don't know if you can see that stippling that we've put there that runs down the Jutland coast and the Bight and across to the Wash, basically, and the Lincolnshire coast, and also down here in what becomes the English Channel. These are the areas where, as I say, there's hundreds, if not thousands, of smaller islands as well. And we know that there's people living out there because there's been quite a lot of material that's been dredged up and washed up, and the Dutch have done quite a lot of work in not only collecting this, but also radiocarbon dating it. And I'll come back to that shortly. Okay, so let's go back to our core. So in the diagram to the right, the yellow shaded bit is the coarse class deposits, radiocarbon dates up the side as well. So we got a date immediately above the coarse sediment, which effectively creates a terminus antiquem for the Storegga event. And that's coming in, broadly speaking, around 8175 years ago, plus minus 25. Now, the structure of that sediment is important. How do we interpret it? Well, you can see there's low energy silts at the base. Then there's a very, very clear and sharp contact with the gravel. Then again, another sharp contact with low energy silts that get deposited immediately on top of it. Now, when you look at the C14 dates, we've dated the contacts on either side, and you can see there's a 3,000-year gap. So there's sediment missing. So clearly what's happened, this wave's come in, it's gouged up some of that surface, removed it, and then deposited the gravel, the high-energy event to shift gravel. So it's a high-energy event that's hitting here, and then deposited that coarse material in the place of the scoured material that's been eroded away. And then immediately afterwards, we've started sedimentation again. Now, when you look at the what comprises that particular gravel sediment unit, the material's sub-rounded, so it's been rolled around a bit. It's not sorted. It also includes sand, and basically all the rock type in there is all the local country rock from the foreshore. So it looks like what's happened, it's the waves come in and it's brought with it all this jumbled material from the foreshore, and it's shunted it further up and up this narrow constricted valley, and then deposited it, probably with the backwash as the waves retreated. The contact, as I've said, is very sharp, so this is an erosive event. There's no lamination whatsoever in there, so it is a single and also sudden event. As I say, we can date it because of that terminus antiquem to bang on the period of the Storegga tsunami. When you look at the nature of that material, you can see the sediment immediately above the coarse sediment, so this nice silty layer here. This is a marine sediment, which means it's deposited in saltwater conditions, and we know that because of the microfossils that were found in it. We've got very good preservation of both ostracods and foraminifera. These are in situ living organisms, and as I say, they are indicating marine conditions, which means that the sea is at that level. And this is contrary to what Sharrock and Hill have been arguing, saying that sea level was lower and therefore trying to cast some doubt over whether the coarse material is in fact a tsunami deposit. But this absolutely proves the point. Okay, and it becomes more brackish as you go up the profile. So I'd then just want to refer to another study that was done. Now, there was some important work by Andy Bickett, Claire Mellett, Louise Tizard and myself, where they did a very detailed geophysical and LiDAR survey of what's called a white ribbon, which is this kind of near shore area, which is normally very difficult to survey because it's so shallow. And what they did, they particularly looked at Howick and Low Hauxley. They did the whole coastline, but they looked at those two areas in much more detail to try and understand the geomorphology and the morphology of those foreshores and what was going on there. There's all sorts of other implications that came out of that research, but in terms of what's relevant for us tonight, let's just have a quick look at Howick. So there's the Howick Burn. And that sandy area you can see in the middle is the estuary. And you can see some of the local country rock there. That's the current foreshore. It's a wave-cut platform. Now, if you go back to 8,000 BP, the cliff line would have been further out to sea. So the shoreline that you see today is not the shoreline of 8,000 BP. That would have been further out. And probably, not too dissimilar from where that current rock platform is, probably going out a few, maybe another couple of 100 metres or so. But this survey extended way beyond that limit and went further out still. And you can see that the deeply incised valley, because as I say, it's 8,000 years ago, it was 7 metres lower than it is today. That's location of the core at the bottom, and we did a second core further up the valley, which got the same sequence as well, I should say. And then you can see the Mesolithic house just up on the cliff top to the north there. And this is the paleo channel in which that site sits, and it's extending out into the sea. You can trace that through the geophysical survey that the team did. Now, tsunamis have a much more pronounced effect at estuaries. And also where you get shallowing and a shallow gradient on the foreshore. And that creates a much, much bigger run-up wave. That is precisely the conditions we have here at Howick. So here's some profiles. They did 3 profiles immediately adjacent to that Howick coastline, and you can see them down here. And what you've got is a series of wave-cut platforms. The first of these probably dates to the late Pleistocene, and then we've got these progressive steps through the early Holocene. Now, that tells us something as well, because if we're getting steps like that, it implies there's been jumps in sea level. So sometimes it's an assumption when you look at sea level curves, because they're nice and smooth, just showing, sea level basically went up during the Holocene. That disguises a lot of variability of what happened in reality. And the way in which sea level rose was probably much more jagged. And what we have here in the geological record is these very clear wave-cut platforms where we're getting jumps, and then, it erodes back, and then jumps again, erodes back. And of course, what that does, that creates a shallow gradient foreshore, which is going to enhance the impact very considerably of a tsunami. So here's that wave-cut platform process. And that occurs, as I say, as a consequence of this ongoing sea level rise, which is also a big, important influence on the Mesolithic population, combined with the landward retreat at the same time as it erodes the cliffs back. All of those wave-cut platforms are below -7 metres, which is lower than that tsunami deposit. So, in other words, what that's saying is those wave-cut platforms were there before the tsunami hit. Okay. And Sea level, okay, as I say, they come with big health warnings, again, because of using these slips, these sea level index points, trying to understand and unpick the interaction between isostatic rebound and eustatic rises and falls in sea level. And the other complication, of course, is Northumberland is on the hinge. So, the south of the county is on the side that's dipping slightly, and the north of the county is going up. So it's doubly complicated. And these are only estimates, therefore. So, as I say, to be taken with a bit of a health warning. But currently, it's thought that the model data is suggesting a sea level of around 6 or 7 metres lower than today. And given that our tsunami deposit had marine sediment being deposited immediately on top of it, and that's 7 metres lower than current mean high tide, implies that 7 metres is probably about right. Okay, so here's a more detailed bit of that model from the Bickett work. And you can see these shallow gradients here extending between 1.5 kilometres plus beyond the estimated 8,000 years ago shoreline. As I say, the other thing that can generate more amplification in the wave height is the valley and the estuary situation, where it effectively has a funneling effect, and the wave will rise higher as it's pushed through. So you've got kind of two things there going on, which will then, create a much bigger wave and bigger impact. This is the diagram for Low Hauxley. I'll not go into that in much more detail, but you can see it's a similar situation. If anything, it could be even worse here because the foreshore, the shallow gradient foreshore, is even longer. Okay, so in a sense, to answer the Sharrocks and Hill question, I mean, it's a very good paper they've done, and but fundamentally, there's clearly something wrong with the model. So they've said, could it be landslip instead? And to be fair, that was another alternative that myself and Ian suggested originally, but we kind of posed that question to try and explore that, and we concluded no, it's absolutely not. The problem is the model doesn't satisfactorily take account of the geoarchaeological structure of the deposits, which I've described previously. It doesn't take account of the micropaleontological evidence, the ostracods, foraminifera, and the marine water above the deposit. Also, the secondary landslip hypothesis wouldn't explain the removal of the sediment, the erosion, and the missing time chunk. They are clear, though, that even under their model, it still could be the tsunami. But what they said was, in order for it to work with their GIS-generated model, which was based on a 6-metre high wave, that would only work during high tide. But the thing is, I think there's a massive underestimate of the wave that's taken place here. And to be fair, they draw attention to this themselves, and they say, look, we modelled 13-metre wave height for Shetland, but the field evidence there is clear. It's nearly 32 metres, so close to 100 foot. So it's 2.5 times bigger than their model suggests. And I think, effectively, we've got a similar situation going on with Howick. And also a storm surge scenario, the problem with that is that wouldn't reach the second reference point we've got further up the valley where we found the tsunami again. So I think, the problem with the model, it's a good attempt and there's a lot in its favour. But the problem is it's not recognising the local conditions and the effect that local morphology, geology is having on the wave itself, and particularly these areas where it would have amplified the wave, such as the embayments, the estuaries, and the shallow foreshores. So there's a bigger picture of the Howick Valley. You can see it. I mean, that's obviously as it is today, but you can see that estuary situation there where that wave would have funneled in. Quickly talking about population then, and the human population. So I was very interested in trying to understand the impact of this on the people. And without being able to find sites where you've literally got, smashed up settlements or, burial of sites, which, there might be the odd site that survives in some way, but it is always going to be a big challenge for us to ever find any archaeology like that. So I tried to come at it from a different angle, and I heard a great paper that Karen Wicks did at a conference in Durham. And what she'd done, she'd used these summed calibrated probability distributions where effectively you sum your carbon dates and you use those as a proxy for human population. So effectively, the more carbon dates, the more people. It's not quite as simple as that, but that's the principle of it. Now, that comes with a massive health warning as well. And these SCPD studies have been, they've come in line for quite a bit of criticism because there's a lot of assumptions upon which they're based. But there's very good reason why we can have some faith in these models that are being produced. And what Karen did, she did this for the northwest coast of Scotland. And importantly, what she did, she compared it with other proxies. So she looked at temperature, she looked at pollen and tree cover, and sea level, as well as then the summed probability distributions for Mesolithic sites. And she got a correlation that is very, very clear, with a huge drop in the amount of C14 dates for archaeological sites from 8.2. So what we did, but she, to be fair, what her and Steve Mythen did, they compared that really with the 8.2 event. So what we did with the northeast coast, we did the same method, but we compared it with not just the 8.2, but the Storegga tsunami as well, particularly given that northeast Britain is in that direct line of fire from the wave. What's happened since then, Karen and Steve have then combined the two studies as well. And it's a very important paper that. It's recent, it came out 2021. And there's a few more dates available as well, since the original work that we did. So, it's got a bigger sample size as well. But effectively the same overall result occurs. I mentioned about some of the health warnings with these studies. One of the problems is, variability in site preservation. The carbon dates we've got, in a sense, only reflect where sites survive. They reflect where field work has been undertaken. So you look at the focus on the Hebrides for the Mesolithic, not surprisingly, there's quite a lot of dates from there, whereas you look at the Cairngorms, there's few in comparison. So, it's inevitably influenced by fieldwork decisions and where people have chosen to do research. Also changes in settlement pattern. What people are doing in the early Mesolithic is very different, and how they're living is very different to how they're living in the later Mesolithic. The landscape is utterly different, and the temperatures and climate and so on. So could those different economic practices and settlement patterns also then create variability in their ability to be located, discovered and dated? And then, of course, there's calibration effects. Where the calibration plateau is going to push more dates into certain time slots. So there's all these things to consider when you're interpreting this data. But the benefit of looking at the Mesolithic is all the sites we're dealing with fundamentally are settlement sites of one form or another. In later periods, from the Neolithic onwards, you've got, burial sites, you've got industrial craft sites, you've got settlement sites. So the problem you have with later periods is you could be double counting people because you're including dates from their burials as well as their settlements. With the Mesolithic, we don't really have Mesolithic burials to date, so it's all settlements. So we don't have that problem. Another thing as well is we have got a good geographic spread here. And when you look at the map I'm going to show you in a minute, you'll see that we have them from all around the north. And the sample size is quite reasonable. When you combine the two studies, I think I've got the numbers in a moment. I think it's 480 odd dates. That's a decent sample population. And all the dates as well were very, very carefully audited. We took out dates with uncertain taphonomy, any that had any question mark about whether they were cultural or natural. if it was poor material, and so on and so forth. So we excluded quite a lot of dates that might have had any potential problem with them as well. It was very, very carefully done. And so this was Karen and Steve's model for the original study, northwest Scotland. So you can see here the different proxies. So we've got temperature at the top, so there's the 8.2 event. Below that, we've got the pollen data, and you can see this crash, absolute crash in tree pollen. Then we've got below that the summation of the radiocarbon dated archaeological sites in terms of the number of sites and then the number of activity events represented by them. So what you're doing there is filtering out a site that, say, produced 10 dates and a site that's produced 1. At the end of the day, if those 10 dates were all very tight and statistically the same, that would only count as one activity event. So, you know, you don't overcount sites just because they've got lots of dates. And of course, Howick is the biggest offender in that regard with 33 dates. And then at the bottom, that's then the modelled population. So what you're seeing is this big reduction at 8.2. And that coincides with these other proxies, these other independent proxies, the pollen and the temperature. And so you get to a point then, well, okay, does correlation equal causation? The thing here is, the two things I think which allow us to kind of get beyond that is there is a clear sequence to what happened, right? So we've got rising sea levels, we've got the breach of the ice wall, the ice-dammed lake at Labrador. Following that, we then get the reduction in temperatures because of the thermohaline current. We get the rise in sea level, the sudden jump. And then following that, we get Storegga. So there's a very clear sequence going on. And also, what we've then got is we've got these sudden changes in independent data sets. So the ice core with the oxygen isotope is thoroughly independent of our C14 dates, as is our pollen data. And then you've got the C14 dates. So you've got different independent proxies, effectively all pointing to the same thing. And when you take into account the sequence and the fact we've got these independent proxies, I think it underscores confidence in we do have a correlation here that is linked. This is the data when we looked at the northeast. That's our activity events, and we've named the sites as well, so it's really, really clear about how we've arrived at that model. And by doing that in detail as well, that got us thinking about their location and very specifically. And I'll come on to that in a moment because that has a bearing on how we interpret this data. And then there's the sum data for the northeast that we published in 2017. So again, we've got so those two blue bands, the left one is noting that 9.3 event, which I mentioned earlier, and then the thicker one to the right is the 8.2. So we've got temperature at the top again, then we've got relative sea level, we've then got the pollen data, this was from Howick, and then down at the bottom the probability events, the activity events, number of sites from the C14 model of the archaeology, and then here the penultimate graph is the population probability. Now, the interesting thing on the northeast, you can see that the reduction happens before 8.2. And there's probably two reasons for this. One that we put at the time is that because the northeast coast is likely to be the most heavily impacted area, we know just from looking at the coastal deposits that there has been significant erosion, which we've seen in the Howick core, of the land surface there. And so it's likely that Mesolithic sites have been destroyed and removed. So it might be that we simply don't have those sites because they've been removed. So what you're looking at there is a taphonomic issue, because in a sense the removal of that archaeology pushes the surviving material back a bit. The other alternative, well, I said the alternative, the other thing that I think's happening at the same time, and Karen and Steve have drawn attention to this, is that what that does correlate with is the draining of Lake Agassiz, so that sudden jump in sea level. And rising sea level, and particularly sudden rising sea level, depending on where you are on which coastlines, can have both a beneficial effect or it can have a very negative effect. And potentially here, it would be a negative effect. Because effectively, if your shoreline retreats, and particularly say if you're backing up against hard cliffs, you're losing the productivity of that foreshore. But there's other areas where, if you get rising sea level, it can actually create new islands and actually then give you more coastline and more foreshore, and then that becomes more productive. But in this case, we think that the northeast coast would probably become less productive. So the population collapse is starting a bit earlier on the northeast, or so it appears, and also tempered by the observation that this could partly be taphonomic because of the erosion of material. But then we get we do have human population through this trough, so post 8.2, albeit at a low level. And then we get the proper start of a pickup at around just after 7,000, just before 7,000, so somewhere around 7,300. That's very important as well, and why it's happening. And that's probably to do with stabilisation of sea levels. Okay, so that's that graph in more detail. Coming on to the combined results for North and East, which is the most recent publication, and it includes additional dates as well. You can see a really good spread of dated sites all around Scotland, North East England, up to Orkney, and there's a couple of dates in Shetland as well. If anyone wants to look at this paper, by the way, it's in Quaternary Science Reviews. It's a very important paper, this. And you can see the graph then that comes from that. So again, at the top, we've got the temperature, then we've got sea level. Below that is some probability and activity events, and at the base is in the shade is the population estimate with the collapse again at 8.2 and just before. And then there's simulations. This is to try and overcome the issue of the calibration problem, to try and look at that by doing dating simulations against what the actual data says. Now, this is if you separate that out, this is then the northeast data again, but with the addition of some new dates since our original study. And you can see again that drop, there is a drop at about 8.5, but it doesn't kind of bottom out, as it were. And then there's a second drop at 8.2. So it could be that, you're getting kind of two hits here, possibly the rise, the sudden jump in sea level, plus 8.2, bang, the tsunami hits. And you get another drop again. And then that's the northwest data, and that correlates more with a 8.2 drop. So that's, again, to do with the temperature reductions and probably less impacted upon by that sudden sea level rise with the failure of the ice dam. Okay, so let's just quickly look at the position of these. This is quite useful. So these are divided into 3 time brackets. The top left is 9.4 to 8.2. The top right, which is the period following the tsunami, is 8.2 to 7,000. And then the bottom left is 7,000 to 5.8. The big dots means more sites. So basically, what's that telling us? There is a movement from the coast to inland in our period following the tsunami. That's, the simple kind of summation of it. And you don't get kind of recovery in the coastal areas until around 7,000. But as I say, if you look in more detail, it's actually a little bit earlier. It's coming in around 7.3 or so. And that correlates what we're getting in terms of field evidence as well, which I'll come on to in a moment. So when you look at the position in the landscape in terms of elevation, again, just to be brief here, the bottom graph, the important thing here, you've got the 3 time periods, which is these 3 columns along the bottom, and you can see in the first period, you've got the kind of northeast, northwest, and then the sum of the 2. You can see that they're at fairly low elevations, 20 metres and lower for the bulk of the sites. Following the tsunami, you can see that the bulk of the sites are at higher elevations, and particularly on the northeast side of Britain. And then it recovers again, and people then come back down, in a sense, and there's more sites at lower elevations from around 7,000 onwards. So this is implying more mobility, it's implying movement inland and people using higher elevation, higher altitudes, and a movement away from the coast following the 8.2, the tsunami and the sea level jump. Now, another bit of important information, I mentioned before, but I'd come back to this, is about the human remains recovered from the floor of the North Sea. So, as I say, these dates have been pulled together by Van der Plicht and his colleagues, and they published this 2016. And very interestingly, there's a heck of a cut-off. So, from about 8,000 years ago, suddenly no human remains. So all the entries above the red line are human remains from the North Sea that are dating pre-tsunami. From about 8,000, there's then a gap of about 5,000 years, nothing. And then the next date, as you'll see there, is Late Bronze Age. And there's just the odd date, Late Bronze Age, Iron Age, RB, and then a lot of modern ones. So these are probably people who've, had an unfortunate fate, maybe going overboard or buried at sea or something like that. So we've clearly got people living out there pre-tsunami, post-tsunami. We have no dated human remains. Now, all these samples are from the southern North Sea. And of course, we have to be very careful about generalisation. And this is something that Simon Fitch and Vince Gaffney have been talking about a lot recently. And they're absolutely right, And we drew attention to it in our 2017 paper that there's going to be huge variation in the impact of these all around the North Sea basin. And this is why these more detailed regional studies are required. So the caveat that comes with all this data is this is very much the southern North Sea and, in truth, just off the Dutch coast, so around the Brown Bank. It doesn't necessarily mean that there was no one left living on Doggerland itself, the Dogger Bank area. But if this is an indication of the general trend, it would point to, effectively the abandonment of some or all of the offshore Doggerland areas following the tsunami. Quickly on Howick, Low Hauxley. So 10 years after Howick, had a go at Low Hauxley. This is a site Clive Waddington looked at in the early 1980s. And basically, there's a Bronze Age burial cairn, although it's Beaker in origin, eroding out the cliff face. It's an awesome archaeological site, and there's a very well-preserved paleosol there as well. It's a complex sediment sequence. So there's 5 metres of dune deposits overlying the archaeology, which we had to remove from the cliff face. So it's quite a big undertaking, this. This photograph, I took this from a helicopter. This is looking down, looking eastwards, looking towards the west, rather. And the modern shoreline is right hard up against the site where the white sandbags are. And you can see in front of that, the seas are kind of like a mid-tidal range there. And you can see, again, one of these lovely wave-cut platforms that's running out on the foreshore. But that shallow foreshore and subsequent wave-cut platforms extend much, much further out into the bay. So again, this is a very shallow gradient, which would have meant a big run-up wave. Okay, why am I showing Low Hauxley? Well, this is about the aftermath. Because at Low Hauxley, we had Mesolithic archaeology pre-tsunami. There was a hiatus sort of in the centuries before the tsunami. And then there's nothing of the time of it, but then we get human activity present on the site around 7,300. And we have that on the archaeological site itself, in the form of some midden material, but also, interestingly, on the foreshore here. And this is the shot that was in the cover advertisement. And all those indentations you can see on that black material, on that black sediment, these are human footprints and animal hoof prints. And people call these intertidal peats. A lot of them aren't, and this isn't an intertidal peat. It's a paleosol, it's a land surface, and it's a woodland soil. And there's evidence, I'll show you, well, there were some photos I didn't include because there'd be too many. But we've got fallen trees, we've got tree stumps in there. This is a forest soil. And those human footprints and the animal hoof prints which are clearly the latest activity on it, we dated the top of it. There was some lovely hazelnut shells and stuff in there, dates to exactly this period, about 7,300. So we've got people identified here on the site, together with animals, recolonising the coast. Why are they doing it, and why are they doing it now? Because this is the period when the sea level stabilises off. So soils develop in stable environments. So we can tell that the sea level has stabilised sufficient for people to think about re-inhabiting the coast, albeit, 700-800 years after the tsunami. And we see that on the site itself. We see it in the foreshore. There's the plan of those particular footprints, but we found them further down the bay, dated those as well. But you can see in this photograph on the right where the site is just above, and that's where the footprints and hoof prints are. And there's some of the carbon dates below. I don't know if you can make it out. On the left-hand photo, just by the ranging pole, you've got a human footprint that's infilled with sand and pebbles. So I don't. It's this one here. And it's clear as well that they had some form of footwear on. So they weren't barefoot. And probably chasing deer. There's deer footprints, there's red deer, roe deer, there's wild pig. There's even some bear scratch marks on some of the timbers where the bears have been sharpening their claws. But the pollen's interesting. Again, just to cut to the chase, the important thing here, looking at the micro charcoal, which is in really quite big quantities. So reasonable confidence in interpreting that as reflecting human activity, and you're seeing that in the pollen from that as well. So we've definitely got people back by about 7,300. Another interesting thing, just to quickly draw attention to on the coast, this is a peat, and this would have been in a lagoon set back behind a dune sand barrier. The important thing to draw attention to on here is we've got the till, which is the grey layer, this glacial till, and again a sharp contact between that and the overlying peat. Now that till dates about 15,000 or so years ago, but immediately above that, the base of that peat is this same period again, 7,300, 7,400. And this isn't just localised, this is all down a 7-mile bay. And it continues, these kind of deposits continue all the way down further south in Northumberland as well. And then they reappear in places like the Tees estuary and so on. What's happened to the missing sediment? Now, it's complicated. I don't think this is, it could be the tsunami, but this is at a different elevation. Bear in mind the Howick tsunami is 7 meters below sea level. This is above modern sea level. But remember, this is further down the coast on the hinge. So this needs exploring, but it's an important question that we need to tackle about what's really going on here, because it does appear that there's been some sediment loss on a big scale. Okay, so evaluating the impact. I'm sorry for the text, but just to try and just keep it focused. So we've got ongoing sea level rise. This is experienced over human lifetimes and would have been noticed. It wasn't just some general background thing that happened imperceptibly. The 500-year gap that we're interested in is estimated as drowning 18,000 square kilometres, which if you averaged it per year, that would be 36 square kilometres per year. But remember, the sea level rise wouldn't just be happening gently like that. It's going to happen in jumps. So some years it's going to be much, much bigger areas. This can have both beneficial and damaging effects for human groups, depending on the morphology, geology of the coastline, and so on. Around 8.2, we've got the abrupt cooling event. It starts a bit earlier than 8.2, that affects the North Atlantic particularly, resulting in sudden sea level rise and a big change to the ecosystem and to the food web. And this would have certainly impacted human groups. Effectively, the conditions are drier, they're colder, they're windier. The next thing is a tsunami. This is a sudden event. It's on a huge scale, and it's shortly after this jump in sea level rise. So it's not just one big impact, it's several. We do have evidence for some buried Mesolithic sites. There's a site at Castle Street in Inverness, which has got a sand lens, which is normally how the tsunami manifests in terms of field observations, and also this site in Norway as well, which is on one of the Norwegian islands. And, you know, we really do need to be looking at trying to find more of these kind of sites and investigating them. We also need to note that abrupt cut-off that I mentioned in the human remains recovered from the southern North Sea, which indicates a sharp reduction in or abandonment of people living out in what is now the North Sea, or Doggerland as it's come to be called. Modelling of the water depth at Howick compared against the tsunami mortality models, this is another important part of the Sharrocks and Hill paper, mean that they estimate 100% human mortality for anyone in that intertidal zone when the tsunami hit. Because modern tsunami studies, what they do, they look at the wave heights to estimate, you know, how many people could die and what the sort of mortality rate will be on different parts of the coast. And if you apply that sort of back, based on their underestimate model, they're estimating 100% mortality within the intertidal. And bear in mind, as I say, it's almost certain their model is significantly underestimating the wave height. A tsunami's sudden onset gives no warning, unlike storm surges, which are accompanied by stormy weather. So people wouldn't have known what was coming. And, you know, there wasn't any sort of prelude to that. You know, Britain is not in a part of the world where tsunamis are a regular occurrence. So there isn't that kind of stored cultural memory and knowledge of what to do and, you know, what preludes a tsunami wave. This Storegga tsunami occurred in early winter. We know that from studies in Norway, where they've looked at the mosses that were found on the tsunami material. So probably around November, December time. This is a time when typically human settlement at the coast is at its a seasonal high, and I think that's more likely the case certainly in Britain. It might not be in other parts of the North Sea Basin, but around that northern British coastline, which is a very productive ecotonal area. And this is also the time when resources are hardest to obtain, and therefore coastal groups are at the most vulnerable at this time. It's also estuarine-based settlement. And of course, these are areas most attractive to past human hunter-gatherer groups, but they're also where the run-up height of the wave is going to be at maximum as well. Those poor people. They really didn't know what was coming. The indirect impacts include damage and removal of resources as well as people. So, you know, it's going to wreck the ecology where you're getting these big impacts. So it's going to affect the fish, the shellfish, the seaweed, the sea mammals, woodland, vegetation. So the whole kind of food web of those coastlines is going to get very badly damaged. And it's going to take a long time to recover. Now, again, that's not necessarily the case all around the North Sea Basin. But on the northeast coast, which is in the direct line of that tsunami, very, very likely the case. And we've seen the effect at Howick where it's removed 3,000 years of sediment. Question then, is there direct evidence for how the humans responded in the archaeological record? At the moment, no. It would be great if we could get that to try and understand, if you like, the human agency side of the equation. What that says to me is we need to get out and keep looking, because you can find these sites. And there's a bit of predictive modelling you can do, because basically the further south you go, the more deeply buried these remains would be. So you should have burial, but the question then is how do you get at the stuff? Obviously the work that people like, you know, Vince Gaffney et al. Are doing in the southern North Sea is very important in that regard. But again, they're often looking at proxies, so, you know, looking at core data and pollen and things like this. But you never know. If we keep looking, we might find a site that does survive and can tell us a bit about how humans may have responded. Okay, so in conclusion, resilience or wipeout? Well, I think reality, it's a mixture of both. And when you look at those population models, you know, this is what they're suggesting, that there is survival, that people are moving away from the coast, moving to uplands, so they're probably changing their economic practices, their settlement pattern, but the volume of population is reduced. Britain, if it hasn't already become so, is clearly an island, you know, by around 8,200 or shortly thereafter. And it does look as though there is, you know, changing Mesolithic trajectories from that point onwards. So, you know, we get the trapeze horizon and so on with the lithics. In northwest Europe, we don't get anything like that in Britain. Similarly, the Irish lithic tradition changes around this time as well. So it looks like there's a, you know, greater insularity occurs as well following these impacts. So there is resilience, but unfortunately there is also, I suspect, on the northeast coast and also on parts of the northwest coast, you know, some very, very rapid reduction in population as well following these events. So were these impacts a catastrophe in human terms? Again, it depends. It depends where you are on the coast. Tsunamis are sudden, they're high impact, they are landscape changing, they're destructive to human and natural life. So therefore, characterising it as catastrophic for our northeast and northern British population, to me, seems accurate and appropriate, particularly when considered in combination with the 8.2 event and the sea level rise jump as well. We do need to investigate, identify and investigate sites where tsunami deposits have been laid down, with a view to identifying the human settlement that may be buried or impacted upon by the waves. Is it a universal impact or regional variation? I've said it a few times. Clearly, we're looking at considerable regional variation. But we need to focus on these regional studies. So, for example, in northern Norway, you know, Blankholm has suggested there, based on, again, looking at his proxies, that actually the 8.2 didn't affect people very much, that there's a lot of continuity there. But again, that's not in the direct line of the tsunami, so it's not surprising. There's also been studies in the southern North Sea where, again, a similar conclusion has been reached. But we need to look at other areas, and it's really worth having a go at these C14 models, because if nothing else, they set up hypotheses which can be tested. The great thing about those C14 models, despite all the problems with those SCPD things, because I was a big, I wouldn't go, well, a positive skeptic, I would have called myself. But what they're great for is identifying patterns, and you can constantly test them. So as you get more dates, you can keep throwing them at the model. So test them to destruction. But we need to look at other areas. You know, further south in Britain, look at the sort of Wales, the Celtic Sea region. We need to look around the Norwegian coast, the Danish coast, the German Bight, Holland, Belgium, and so on. And inland dates are just as important, because we need to know where people are going as well. So I'll conclude there. Here's a few publications that are relevant if people are interested. There's a rogues gallery at the top. So we did the very first series of Coast that came out. We rebuilt the Howick house for that. And this was at the start of the career of Alice Roberts, who's there. My good friend and colleague Ian Boomer, who's next to her. This is Claire Headley, who is the head of climate change at Historic England. And then in terms of the digging team, we've got Rob Shiel over here as well, who's an earth scientist who contributed. And of course, our good friend Nikki Milner here, who was my co-director on the Howick project. There's some of the publications. You can download the Howick volume now as a PDF. You can get it off Oxbow or our website, so it's easy to get hold of now, which is good. And really, thank you. I'd like to thank particularly Ian Boomer for the work he's done with me, and particularly with regard to the tsunami. Also, you know, the work of Karen Wicks and Steve Mythen and the work we did together on that. They've done some really great work, and that 2021 paper's really worth reading. And then really just all the other earth scientists and archaeologists who've done so much work on this topic. These are people, you know, all across Scandinavia, particularly Norway, Germany, Netherlands, and also all across the UK, much of whose work I've drawn on, and who've done some really good sterling work. It's an exciting story, this. There's still more to be found out. We still need more field work in all regards. And it's been an absolute pleasure to be part of trying to unpick this fascinating story, really, of how Britain became an island. Thank you to all the people who sponsored and funded those excavation works as well, because without them, we couldn't have done it. Thank you very much.